Hello and welcome to this introduction to reactor fluid mechanics. Now, fluid mechanics, as it sounds, is the study of fluids, and those fluids can be either at rest or in motion. If a fluid is at rest, we call that hydrostatics. Hydro for water and statics for still. We can also look at fluid kinematics, which talks about what's flowing where. So that's when we're looking at velocities and flow rates and things like that. And then last of all, we look at fluid dynamics. And fluid dynamics looks at the forces that are acting on a flow to create the specific flow. Now, fluid mechanics is a primary engineering science. Almost all engineers use fluid mechanics for part of their job. And it has applications throughout modern technology. We can look at aerospace, we can look at mechanical systems, power use and power generation. We can look at biomechanics for artificial hearts and artificial joints and things of that nature. We can look at meteorology, we can look at climate science, and many other fields. So, as some examples, we can look at the designs of canals and levees, like those that failed during Hurricane Katrina or the flooding in Missouri a couple of years ago. We can look at the design of piping systems in nuclear power plants, like the AP1000 and the ESBWR. These new plants have used fluid mechanics and other design principles to reduce the complexity of the system and increase its safety. We can also look at aerodynamics of automobiles to try to increase fuel efficiency and reduce energy use. We can think about environmental and energy issues through the lens of fluid mechanics, looking at containing oil spills, wind turbine performance, using wave energy or tidal energy, or again, analyzing the climate. We can look at artificial hearts and valves. It turns out there's no actual biological requirement to have a heartbeat. It's a consequence of the fact that we use a volume displacement pump for a heart. When we decide to design an artificial heart, the existence of a heartbeat becomes a human factors design choice. It's not actually necessary for us to survive, but having a heartbeat makes people more comfortable. In fact, it would actually be easier to design a rotary pump that has no heartbeat to replace your heart. Mechanically, that would be much simpler and much more durable. However, it would make most people uncomfortable. We can also look at athletics, looking at bicycle helmet design to reduce drag on professional cyclists, looking at golf or tennis and the drag on the golf ball or the tennis ball to try to improve the flight and the performance to bring down your score in golf or make the ball go faster in tennis. We can also look at swimwear. In fact, Olympic swimmers have reduced their times significantly over the past 20 years or so, and part of that is because fluid mechanics was used to design their swimwear to reduce drag on the swimmers so that they could swim faster. Of course, this is a course on reactor fluid mechanics, so we're going to focus a lot on nuclear reactor designs. And there's various nuclear reactor designs, but one thing they all have in common is they use flowing fluid to move energy from one location to another. And so in order to understand these systems and design them to work properly, we need to understand the mechanics, the basic science behind how these fluids are moving from one place to another. Now at this point, we're just going to do a brief review on some introductory concepts. So we're going to start with the characteristics of matter. And you guys have seen this before, I'm sure, but we're just going to take a moment to review. And we start out with solids. Now solids maintain their shape and their volume because their molecules and atoms are held very tightly together. And in fact, they behave much like springs. They deform a little bit if they're put under stress, but when the force is removed, they bounce back. Liquids, however, flow to take the shape of their container. They don't maintain their shape. They do, however, resist compression. So it's very difficult to compress a liquid because the molecules and atoms are already pretty close together. Now, gases are like liquids in that they flow to take the shape of the container. However, they're not like liquids because they can be compressed. So you can compress a gas to increase its density and pressure. The last version of matter here is a plasma. A plasma is basically an ionized gas. It can be either at very low pressure or very high temperature. Now, a solid is not a fluid. It doesn't continuously deform. But liquids, gases, and plasmas are all considered fluids. Now, the reason for that is a fluid is defined as a material that cannot sustain a shear force at rest. That means when you push on it, A solid or a fluid will deform a little bit when you push on it. However, eventually a solid will resist that, and it'll push back. A liquid will just continue to deform and move under the same stress. So a solid has a definite strain for a particular stress. A fluid has a continuous strain for a constant stress, which means the strain will continue to increase over time. So in solids we use strain and stress, but in liquids we use strain rate and stress. The strain rate is the change in the strain with time. So even very small shear forces can cause a fluid to continuously deform. They'll never reach a rest state while they're subject to a force like that. Now, within a fluid, we can look at different ways of describing a system. So we can look at a system as a particular amount of something that we're studying, and then the surroundings is just everything else. So a control mass is a system that's composed of a fixed quantity of mass. So we look at this and we see that there's a certain amount of gas inside this system, and the mass of that never changes. Nothing ever moves in or out. So energy is allowed to cross the boundaries of a control mass, but matter is not. So heat can flow in and out, but mass cannot flow in and out. The boundaries, however, can move. So this means if you're looking at a control mass, you're always following the same lump of stuff. We can also look at control volumes. Now, a control volume is basically an arbitrary section of space. In this case, mass and energy can both cross the boundary. So you can have mass coming in, mass going out, heat coming in, heat coming out. All of it is possible. And the boundaries, of course, can move. You can have a moving control volume. Now, for both the control mass and the control volume, we have a control surface. The control surface is the boundary of the control mass or the control volume. And it actually has an orientation or a direction. That direction is defined by this outward pointing normal, this n hat vector. It's always perpendicular to the surface, and it always points outward from the control volume. We're also going to talk about properties, and properties are just characteristics of a system that we can see and measure. Extensive properties depend on the amount of mass that you have. Mass itself is actually an extensive property. Intensive properties are independent of mass, things like pressure, density, or temperature that don't depend on mass. Specific properties are properties that are per unit mass, things like specific volume or specific enthalpy, where you have the amount of something per unit mass, volume per unit mass, energy per unit mass. Now the state of any system is its configuration, and we describe the configuration by the properties. So when we're talking about the state of a system, we need to include sufficient detail to distinguish it from other possible configurations. So if we're considering the state of a fluid, for instance, we look at the density and the pressure, or the temperature and the pressure, or some combination of properties that define the state. Now, we can represent a property by what we call the field representation. It's just a function that's a function of position and time that gives the value of whatever property we're interested in at all locations and all times. In this case, we look at the field representation of density by some function. Now, we have scalars, which are quantities that have only magnitude, like density, but we can also have vectors, like velocity, which has both a magnitude and direction, and is a function of position and time. So we have to address all of these different things, and we'll begin doing that over the next several videos for this course.